Voyage Home. So we got a big spaceship shaped like a cigar, and it's a little thing down here. If you haven't seen Star Trek: The Voyage Home, it's my favorite. It's the one where they save the whales. You know, obviously, kind of a hippie. I like people saving whales and peace in space and stuff like that. But the aliens, they built this giant spaceship to, not to spoil too much. The movie's been out for like 30 years. So the aliens built this giant spaceship, and it gets to Earth, and it has this signal that it's shooting out from this thing. And this signal goes out, and it's screwing up the whole Earth. And they think, well, we've got to answer this signal. So this thing stops destroying the Earth with its rays, right? And this signal, and they figure out, you know, that it's a signal designed to talk to whales. But in the future, oh no, whales are extinct. So they have to go back in time, rescue whales, and then bring them back to the future. That's the plot of the movie, Star Trek IV: The Voyage Home. But it's got this really big spaceship that's shaped like a cylinder. Okay, so what if we wanted to find the gravitational field of this spaceship? Well, what we would do is we would, mathematically, is take a test mass of mass m. Test mass. Right? This spaceship over here that's got the big mass, right? So this test mass is going to feel some gravitational field pointing at that. And the reason we do this is to get rid of this other m. So g as a vector, this will be the gravitational field. Right? Perhaps not the best convention, because we also use this for the gravitational field near the Earth, but this is, we call this the more general version. So what acceleration does this test particle feel? Right? We call that g, the gravitational field. And again, the reason we do that is just to get this m out of the equation, so we talk about this as an acceleration. So the gravitational field is an acceleration of a test particle, right? The acceleration that this test particle of indeterminate mass m feels as it's somewhere around in this space, right? So we can just say that's Fg over m, or we don't worry about what this mass actually is. It can be anything, right? We've seen before that m's cancel out when we talk about dynamics. So this is a vector quantity, right? Which means that if we want to know the total gravitational field due to some object, I add up all of the individual pieces of that gravitating object together as vectors, right? So this is the same sort of thing we've seen multiple times in this class. For example, when we were talking about center of mass, we had a similar thing where you imagine lots of like point particles, and then you add them up, and then you get the center of mass of the whole system. Here, we might imagine breaking this alien spaceship up into a bunch of different point particles, and we add them up, and we get the total gravitational field of the alien spaceship. And then you are probably already seeing this coming, right? That if I have not some discrete object made up of little point particles, but a continuous object, gravitational field is then given by an integral over that object. So, fortuitous that I said it's a rod-like alien spaceship, because the problem we're going to go through is finding the gravitational field of a rod like this. Okay. So let's do an example of finding the gravitational field. So we have our coordinate system. So this is going to be pretty familiar, but with extra complications that will be new. And just for fun, I'm going to say this is still a little. Go watch the movie if you haven't seen it. It's funny. You know, they go to what was present day when the movie came out, which is, you know, the 80s, and they go to San Francisco and they get in all kinds of hijinks and stuff like that. But, you know, it's a good movie. Go watch it. And maybe it'll be an extra credit question. Yeah. Okay. So we've got our little test mass here, so we're going to call that P. And this is going to feel some infinitesimal gravitational field, right? Some infinitesimal gravitational acceleration pushing in this direction from a little infinitesimal slice of this alien spaceship. Right, so now this should start to seem a little bit familiar, right? That we're adding up little infinitesimal slices of this object, and each little infinitesimal slice, let's call that, what is the dm? So this is dm. This is dx. So we're looking at little infinitesimal slices of this object and the field they each generate on this test mass, on this point particle P. So we're going to say this x is now xp. This is the x-axis, obviously. And it's a little complicated to draw, so give me a moment. Okay, so this thin rod, alien spaceship, is length L. Despite the way I've drawn it, imagine that it's halfway, right? That it's L over 2 over here and L over 2 over there. Now there's 3 distances involved in this calculation, which makes it a little confusing. There is the position of this point particle P, right, which we call x of P. And then the distance, of course, from the center of the object to there is xp. We also have xs, which is the distance from the origin to this infinitesimal slice, right? So this xs, this is the variable we're integrating over, because as we vary xs from minus L over 2 to plus L over 2, we're adding up all the little slices and their gravitational field on the point particle P. And we're going to say this thing has some mass, big M. And the last distance to talk about is the r distance that we use in our Newton's gravity equation, right? And 1 over r squared. That r is going to be the distance between the slice and the point particle P. So we've got xs, which we will integrate over, the position of the slice. We've got xp, which will be a constant, which will just tell us where that point P is. And we've got r, right, which is going to be some function of either of these things. That is going to tell us how far is that slice from our test particle, and thus how strong is the gravitational field of that individual slice. Okay. So the next thing to do is define the dg. Right, so since we're just talking about the x direction, right, this becomes significantly more complicated if this thing is off the axis, so we're just taking the simplest case. It's just you'd have more geometry involved and probably a more difficult integration. So we're going to have this dgx equal to negative g dm over r squared, right? We don't have the mass of this object because we had that whole thing on the last board, slide, whatever you want to call it, that, right, the whole point of having a test particle is that so that goes away. So we have just the mass of this little infinitesimal slice times the gravitational constant divided by r squared. And that dm, of course, and this should be very familiar, is just lambda dx. The volume along one dimension, the dx times the density lambda. Okay. And then that lambda, of course, for an object of constant density is just m over L. Right, the mass divided by the volume length. So now, since we need this r here, we have to find this r here. So that's pretty easy. R is just xp minus xs. So some constant minus a variable. So then if we were to write now this dg again in its full glory, we get negative gdm over r squared equal to negative g lambda dxs, right? This is the variable that we're integrating over, this xs, the position of this slice. Should probably have written that there too. Divided by x of p minus xs squared. Okay. And then if we want to know that gx, this is just the integral of dgx. So we plug that guy in, set our limits, which of course are negative L over 2 and L over 2. So the endpoints of this object, right, we integrate over the object. And then xp minus xs squared. Where'd it go? Oh, shoot. Lambda dxs. Okay. So I'm not gonna do this integral because we're actually pretty short on time. But these guys are constants; they come out. Here we have to solve this with a u substitution, right? If we went u equals xp minus xs, and du is just then going to be negative dxs. Right? We do this u substitution. We do the simplification. Hopefully you guys are at the point in your calculus class where you don't know how to do u substitution. If you don't, maybe go ask me on the forum and I can explain it, or maybe do this in more detail next video. So we then do this integral, and I will also skip over the algebra. We have g equal to, well, let's put it as a vector, negative x squared minus L over 2 squared I have. Okay, for x greater than L over 2. Right? This doesn't work if we're somehow trying to find the gravitational field inside this object, right, in the hallways of this alien spaceship. If they have hallways. Maybe they have just tanks of goo, right, and the aliens live in goo. Who knows? Yeah. So we have negative gm I hat x squared minus L over 2 squared. Okay, so that's the gravitational field along this line where we have this test particle P. Okay. So maybe it's interesting to close out talking about gravity by talking about the deeper level of what it is, right, conceptually. So perhaps some of you have been thinking, well, objects generate this field, whatever that means, and this field is out in space even though we can't see it, and it creates these forces. This seems sort of mystical almost. No, but it's not, because we've been working on this for a while, and Einstein in the early 20th century came up with the general theory of relativity, right? So actually the next class or two, we're going to talk about the special theory of relativity, which tells us how time works when we're moving at high velocities, and also how distances work when we're moving at high velocities. And spoiler alert, it's different. General relativity tells us that what we perceive as gravity is actually a curvature of space-time. Okay, so what does that mean? Okay, well, let's imagine, now let's draw this better. Let's imagine we've got a trampoline. Oh, God. Not even close to it. Yeah. Okay. This is our trampoline. Okay, we're looking at it kind of from above. Okay, it's got maybe some lines painted across it for some reason. Okay. So the trampoline with nothing on it and nothing happening is kind of like empty space. Flat. No influences, no gravitational fields. This is a universe free of matter. And just flat space-time. Maybe there's some light beams shooting around inside of it. Okay. So empty space is like the flat trampoline. Now imagine I place a bowling ball into the trampoline. Well, that bowling ball is going to make an indentation in the trampoline. So now those lines that were straight before kind of look like this. We've got this indentation in the bowling ball we got this indentation in the trampoline caused by that bowling ball curving the trampoline around it. Okay. So before we had that flat trampoline, if I put like a light little marble that didn't make a dent in the trampoline on the trampoline, it would just stay there. That's like the a small test mass in a flat space-time, right? There's nothing to gravitationally attract that marble, so it just sits there. Now what happens if I put a marble on this trampoline with the bowling ball? Well, that marble is going to fall inwards towards the bowling ball because that's the way the trampoline is curved. Okay, so this marble is going to follow the curvature of that bowling ball. Likewise, instead of I just put it there and let it go, I could maybe give it some extra velocity, right? And then it might circle around this bowling ball, might orbit around it, right? So this is like, I don't know if they still have those, but I haven't seen one in years, but those little things they have in supermarkets for donations where you put the coin in and it goes, and then it goes down into the funnel, right? So that's sort of like this. That's sort of like what an orbit is. We have this curvature of space-time, and then orbits are like flicking a marble around, and that marble orbits around this curvature of space-time. So it is the nature of matter and energy to cause curvature in space-time, and it is that curvature that we feel as gravity. Okay, so I mean, this is like a year-long graduate level course to talk about this, other than just the concepts I've talked about. But if you have any questions or are interested in it all, please ask me some questions on the forum. I just wanted to give you just a little bit of a flavor of our modern understanding of gravity, so it doesn't seem like some mystical, mysterious thing. There is an explanation for what these forces are. Well, then, I mean, there's obviously more mysteries as you go deeper and deeper in, but I mean, we won't get to them in this class, unfortunately. Although we'll see some interesting, mysterious stuff in the next lecture or two when we talk about special relativity. Okay, and then you might ask, well, okay, if space is curved, through what dimension is it curved? Well, it's curved through time, right? So this, what is in principle a three-dimensional drawing, right? Because I'm trying to draw some third dimension in the curvature. This three-dimensional drawing would represent a two-dimensional space-time. We would have an x-coordinate, a y-coordinate, and then the perpendicular coordinate would be time. Okay, and there's all kinds of weird things that this implies. For example, that when you have more curvature through time, you actually have time ticking more slowly. So time ticks more quickly further away from gravity. Time ticks differently when you move at high velocities also, as we'll see in class. Okay, that's even just a little bit over time. So hopefully this was interesting. Obviously I'm not going to test you on general relativity, but as always, any questions, please feel free to ask. I hope you are all doing well. Sorry this is going to be uploaded a little late over spring break, but you still have all that time to do your homework, so no extra homework. I guess homework would probably be due Wednesday. Have I assigned homework? I'll go before I ignore what I'm saying now. I'm gonna go obviously check before I write you the email to say that this lecture is up. Okay, hope everybody's doing very well, and have a good Easter break, whatever you end up getting up to. All right, bye-bye.